Hello everyone, this is Abhishek Gade and today we will be talking about inlet-outlet boundary condition in OpenFOAM. So let us start. So what are the prerequisites to watch this video? Please see the mixed boundary condition in CFD OpenFOAM because we are going to derive this boundary condition from that boundary condition itself. So if you know mixed boundary condition, then it would be really simple. So what is inlet outlet boundary condition? Let's begin. So inlet outlet boundary condition is an outlet boundary condition applied at outlet, and it is derived from the mixed boundary condition. So all the variables which are there in the mixed boundary condition, we will set them to certain value. It will be user specified or specified by the computer, and then it becomes the inlet outlet boundary condition. So why the need for this? So this is needed when there is a reverse flow at the outlet. Okay, so it can be used for any type of variables. Okay, we can say like scalar variable or vector. Okay, and for reverse flow, what we'll do is we will fix a value that is specified by the user. So user is going to specify a value for any reverse flow taking place at the outlet. But for outflow, the code itself applies zero gradient boundary condition. This is applied by the computer directly, the zero gradient boundary condition. So GB in the, if you remember the mixed boundary condition, the equation for mixed boundary condition, no issues. I am going to write that equation at the end. So I'll show how we are implementing this inlet outlet using the mixed boundary condition. But to just let you know, like these three variables were there even in mixed boundary condition. That was, one was gradient, the one was the value at the boundary, and one was value fraction. This is directly set to 0 by computer code. So for any outflow, zero gradient is set, and we'll see what is this inflow and outflow, what is this reverse flow, just in some minutes. Like, okay, so what is the usage, how we can implement in OpenFOAM? So this is the syntax, the formula. So we'll write patch name, and in curly brackets we will write type inlet outlet. Inlet value is field value, we'll specify whatever the value we want. Then this is the one which is specified by the user. Okay, gradient is directly set to 0, so there is no need now to write here. If you remembered, in mixed value we had two things, reference mixed boundary condition, we had two things, reference value and reference gradient. Here we say only inlet value we have to mention, but in contrast to that, why? Because already we have specified zero gradient in the code, and value is set to some value. So what is the difference between inlet value and value? So value is the initial value at the boundary. So at the zero time step, you can set some value, and after that it will change according to whatever the it is influx or outflux. But this initial value you can specify in the simulation run. And one optional entry is phi. So what is a phi? Phi means nothing but mass flux or volumetric flux. Now don't get confused by this term phi, because till now in all our boundary conditions we have written phi as a variable. But if you remember, in the zero gradient boundary condition video, while discretization, I told you at the end, like f is the flux, f. So this phi is nothing but f for us right now. So please consider this convention only. So F is the flux. Um, it is the dot product of velocity and area. Yes. So velocity and area dot product, or we can also multiply it by density. So it is nothing but the volumetric flux or the mass flux. Okay, so but reverse flow we are talking. How does it consider the reverse flow? We need to check the direction of flux. So see, we already know this two diagrams from our previous boundary conditions. Still, I'll go through it. So at the center, we have phi p. The variable value has the value of phi p. Here at the face, at the boundary center, we have phi b, and the surface area normal is SF, and the distance between two is magnitude d. Now, see, in this inlet outlet boundary condition, we are not interested to see how the discretization takes place, how the final discretized term is calculated. We are interested to know what will be the phi b, and we can directly then put that value of phi b inside the discretization terms that we already have done, like in zero gradient boundary condition. So no need to do here. We'll just find what is phi b. Okay, so see, outflux. When I say outflux, means something is moving out of the domain, out of the domain which I have prepared. So see, it is moving out. And when I say influx, see, something is moving inside the domain, that is influx. See, the outflux direction is in the direction of this SF, that is the surface area normal, and this is in opposite direction while it is in influx. This is called as the reverse flow. Okay, so yes, let's move forward. So yeah, before moving forward, we'll have to initialize all the variables. So the reference value is set from what we type, what we give the value inside this inlet value, which I just now showed you, and that is equal to phi b. The reference gradient is set GB, that is set to 0. And this is going to be permanently set as 0, we know that. And the value fraction is set at initialized at 0 in the beginning. But here is the trick. Think like this. Something is going out, something is going in, and according to that, I need to change the signs. I need to, how will I know like the reverse flow is there or if the reverse flow is not there? The trick is this PosZero function. So let us first understand what is PosZero function, and then we will implement it in our code. So what is the PosZero function? Let us take a scalar, any scalar variable s, and if my s is greater than equal to 0, then my function gives the value 1. If my s is less than 0, then the PosZero function will give the value 0. Okay, so this is simple PosZero function, how it is defined in OpenFOAM. Now let us implement it in our case. Okay, remember this phi p is nothing but flux, that f, that flux. Okay, the phi which I told, it is same as that only. Now if I, in place of that scalar variable, I am just writing phi p. Okay, s. Just now we have learnt about PosZero function. So if my phi p is greater than equal to 0, the PosZero function will give 1. And if my phi p is less than 0, then the PosZero function will give 0. Now why, when is phi p greater than equal to 0? Means it is moving out. It is moving out. Outflux is there that time. And when it is phi p less than 0, when it is moving inside, phi p is nothing but phi, the mass flux or the volumetric flux. If the surface area normal and the flux direction is different, then phi p is going to be less than 0, negative. Means something is moving inside the domain. And this is how the value fraction changes if there is an outflux or influx. And see, this is the trick. The value fraction is changing, and this shows, this will give our implementation of zero gradient or the fixed value as set by the user. So what we see, the value fraction f is equal to 1 minus PosZero 5p. So 1 minus 1 is going to give 0, and 1 minus 0 is going to give the value 1. So value fraction takes a value of 0 when it is an outflux, and value fraction takes the value of 1 when it is an influx. So this is how it is implemented in the OpenFOAM code. Value fraction is equal to 1 minus PosZero 5p. And yes, we have all the things now what we want to finally understand this inlet outlet boundary condition. So above you see the mixed boundary condition equation. Uh, you'll have to look into this video of mixed boundary condition. So phi f, their face value should be equal to the value fraction multiplied by phi b. So plus 1 minus f into the nearest neighbor cell center plus gradient into the distance. So let us now take two cases. One is outflux and one is influx. Outflux means we had the value fraction 0. We just now saw it. And influx means value fraction f is equal to 1. So when there is an outflux, but we also know we have already set the gradient as 0. So when f is 0 and gb is 0, this whole equation will finally turn out to be this equation only. That is phi f is equal to phi p. So whenever the uh, the flux is moving outside the domain, your value of the phase would be equal to the value at the center. The value of this boundary, the flux passing through this boundary in case of outflow should be equal to this, equal to the phi p, the cell center, the variable values. And yes, this happens, and it is, yeah, it's correct because there is a zero gradient, so the values of both would be same as we have learnt in the zero gradient boundary condition. And but what about the influx? Then in the influx, what we see, if we keep f is equal to 1, which we just now saw after implementing PosZero function and all. So if f is equal to 1, this 1 minus 1 is going to become 0, and only this term will remain. F, let's put f1. So phi f is equal to phi b. Okay, so whatever the user specifies the value at the boundary, that phi f would be equal to the phi b. Okay, so again, this is like a fixed value boundary condition. So see how this inlet outlet boundary condition works. So for reverse flow, user is specifying the value, but for outflux, when the flow is moving normally outside the domain, we are directly taking the zero gradient boundary condition. This is the definition of inlet outlet boundary condition. But then while doing, you might get confused. So don't get confused. See, let's take an example. So this is a dam break case from the OpenFOAM tutorials. So this water, this is a water in the dam, and now that dam has been, so dam is breaking up. Like, okay, so what happens is this water is going to flow like this. It's just going to splash down. Now what will happen? The above air is going to come inside. So in this region, in this up region, in the left side, there would be some air that would be sucked up down because the water is flowing down. The water is flowing down to fill this area. That is why the some air should be sucked up from here. Now, what is the problem? That what to keep inlet value? So people like what I also felt in beginning, let us keep only one uniform 0 1 0. So this is in y direction. Okay, so if I keep y, inlet value will directly point inside the domain, but no, it is not like this. See the two different cases here. So in first case, I kept inlet value as 0, -1, 0, and inlet value here I kept uniform 0, 1, 0. So see, yeah, this is wrong. When I keep 0, 1, 0, inlet value means it won't directly point inlet. You will have to keep the sign also 0, -1, 0. Then only it is going to point inside negative y direction. It will point. Don't go with this word inlet value, else you are going to get confused. Inlet value is just a term, but as you saw right now, it is same as fixed value boundary condition whenever there is a reverse flow, and for that you will have to give this value, and also be careful about the sign also which you are giving. Inlet value means it should be then negative then. Okay, so this thing needs to be taken care of. Again, this boundary condition is not so suitable for a reverse when I'm talking about the variables such as velocity. Why would there be a problem? See, why would there be a problem? Because if there is a suppose there is a reverse flow, which fixed value should I give for the reverse flow? So confusing. We don't know what value should we give for the reverse flow at the outlet. uh, Rather it won't I have a question, like rather won't it would have been better if we would have kept zero gradient only at the outlet? So uh, whatever the vectors are pointing inside, the same value would have been given to the boundary. But no, this boundary condition doesn't consider this. It wants an inlet value in case of reverse flow. Means we need to specify that value. That can be right also, that can be wrong also, we don't know. So but yeah, there are other boundary conditions which will improve on this boundary condition, and then we can use it. So that is for later, like I'll tell you that in future. But for this, for right now, this is all about the inlet outlet boundary condition. And yeah, thank you. So if you liked my channel, if you like this video, do support me at the PayPal. Don't forget to subscribe my channel, and if any comments, do share me what videos you require, whatever you feel about all these videos. Yes. So thank you. Thank you.